Okay, we're good. Okay, so this part should be a review for you guys. Plus, if you guys were in the very first session of SI, we kind of like covered this, like on the whiteboard. We were just talking about this and RU. So does anyone just remember off the top of their heads? Like, do you guys remember those reactions? Do they look familiar? A little bit.
Yes. Oximer. Yeah, I definitely remember that.
He does, but I don't.
Hydroboration.
Hydroboration.
Acid catalyzed hydration.
Do you remember that
I
one?
have to.
That
Is the OH go on the more substituted?
For which one?
Acid catalyzed hydration. No. Less substituted on acid catalyzed hydration. More substituted on oximer dimer.
No,
Oh,
not quite.
so where does the OH go for acid?
Okay, so let's start with the basics. So first of all, in case you want to read your notes from Orgo 1, this is chapter 8.
Yeah.
Okay, this is chapter 8, so that means addition reaction. So we're going from double bonds to single bonds. And then remember, how do we go from single bonds to double bonds? What's the kind of reaction that we do?
Eliminate.
Eliminations, exactly. We're going to be talking about those next. But let's start over here. Okay, so before we talk about the reactions, each of them is going to have like a set of rules, right? Like Regis selectivity, stereoselectivity. What's Regis selectivity?
Where it has RNS. Oh, wait, it's like it's all one reaction, so it.
That's stereoselectivity. Syn and anti-addition are stereoselectivity. Beautiful. Okay, let's talk about Markovnikovs first. What's Markovnikovs? What does it tell you?
favors the more substituted product.
It makes you add the OH to the more substituted side of the double bond. Yeah.
So what's the other thing? The two Hoffman and
Hoffman and Zaitsev, those are for elimination
Right,
reactions.
okay.
Yeah.
So Markovnikov, what is it? You put it to the more substituted side.
You said this is addition reaction?
They are addition reactions, yes. All of the chapter 8 reactions, they are addition. But let's start writing them here, actually. Let's write Markovnikovs. And it's a little too thin. With the dog and the cat, not yet. I'll upload it. Don't worry, you're gonna get my dog and my cat there. But yeah, in case you're rewatching this, like in the recording, remember, dog, first exam, cat, second exam. If you see both of them, you're gonna see them in both exams. Okay. Question in the back. Yeah, so Regis selectivity is just about Markovnikovs or anti-Markovnikovs. And it's talking specifically about the products, what kind of products you're forming. But as far as Markovnikovs go, that's just the rule that tells you that you're adding the OH group to the more substituted part of the double bond. Okay. So let's quickly start reviewing those reactions in here. Now, we know that anti-Markovnikovs is just the complete opposite, right? So OH goes to the least substituted side. That's it, right? Okay. So let's start with the very first one, which is your acid catalyzed hydration. So the reagents that you have to memorize is basically just any sort of acids, okay? Especially H2SO4, like that's the most common one that you're gonna see. Whoops. But H2O and just normal hydronium ion, they count as well, okay? So keep that in mind. Okay, so let's fill up the rules before we do the product. So Regis selectivity wise, what's the rule? Markovnikovs? It is Markovnikovs, yes. So that means that I'm adding the OH to the more substituted side. Now, what about stereoselectivity?
Yeah.
It doesn't matter because we don't have a preference for this reaction. So there's none. Okay, rearrangements.
Yes, ring expand.
That's one of them. What are the other two types?
Hydrogen and
There's one. Beautiful, you guys got it. So yes, you have rearrangements. Beautiful. Okay, let's talk about the product in this case. So for this class, you guys are not gonna get asked about the mechanism. You just have to learn how to identify the initial molecule reagent and what's gonna be the predicted product. So in this case,
that is the reaction.
that is a reaction, but you don't have to like see like step by step, like the curve there mechanism, like lumbers to this. What's the intermediate? All of that. It's not gonna be like that. Okay, so we're skipping the complicated part, let's say. But okay, in this case, as far as the reaction goes, what's gonna make the first attack? Do we remember?
is it gonna break that pi bond?
Yeah, the double bond's gonna swing open and grab.
Exactly, yes. So for any addition reactions, the double bond is always gonna act as the nucleophile, meaning that it's gonna do the first attack. So yeah, double bond would just attack your acid or whatever you have in there. And then of course, that's gonna create the carbocation, right? Now, remember, this is a Markovnikov's reaction, so that carbocation is gonna go to the more substituted side over here, which eventually that's gonna be where we're gonna add that OH group, right? But remember, whenever you have a carbocation, you have to check the stability of it. What's the most stable carbocation that we could have?
Tertiary,
Then,
secondary.
and last one, primary. There's something more stable than just tertiary.
Quarter. You can't have.
That wouldn't be a carbocation, yes. Allylic positions, exactly, because of that extra resonance that you have.
Oh,
So allylic, tertiary, secondary, primary, and then do you guys remember vinylic?
a little bit, not really.
Vinylic is right next to it and it's no good.
Yes, it's not good. That's the only thing that you have to remember. Vinylic, it's not good.
Could you draw a little like?
Yeah. Let's do it here, actually. Allylic. It's just, for example, let's say that's my double bond. And I'm looking at that hydrogen, for example. That's the allylic position. And then vinylic
Where would the carbon kind of?
is where the carbocation is. I mean, yeah, you can just replace that hydrogen for a carbocation.
Oh,
But
I
yeah.
see.
Vinylic is directly connected to the double bond. But okay, let's go back to this. So in this case, oh, I'm sorry. Yes,
So question for this molecule then, so we have a tertiary, but we also have like two vinylic positions, but because we have, or not vinylic, allylic position, right? But because we have a allylic that's a secondary, that's gonna be where. second hydrogen-
no, because remember that once we create the carbocation, we're getting rid of every single double bond. So there's no allylic position at all. You guys just have to remember the allylic position because of something that we're going to talk about next. That's why. But in this case, remember, once the double bond does the first attack, that pi bond is going to be non-existent. It's going to be gone. So therefore, there's not going to be any allylic position. But we know that after the first attack, that's going to be when we create our carbocation, right? Over here. That's going to be the intermediate. Do we have the most stable carbocation that we could possibly have?
Yeah, yes.
Yes. So that means that once I have the most stable one, now we can just slap that OH into that carbocation and that's it. You don't have to do anything else. You don't have to show the curved error mechanisms. So in this case, that's going to be your product. We're preserving the carbon skeleton because we're not doing any rearrangements and we're just slapping that OH into the more substituted side. Questions on that one? We're good? We remember the reaction now a little bit more?
It's getting there.
It's getting there. Okay, we're getting there. Okay, let's quickly talk about oxymercuration, demercuration. So of course, like just you can hear in the name, like you have mercury. So as soon as you see Hg, that's gonna be your reaction. But let's talk about the rules. What's the Regis activity? Anti-Markovnikovs, do we agree over here?
That's.
No?
Real quick, for H3O, H2SO4 is also a viable.
Or yeah, as long as you have any sort of acid, like the most common one that you saw in Article 1, it was H2SO4. But in this class, you can also see like H3O plus, H2SO4, like any of those guys. Okay, it's actually not going to be anti-Markovnikovs. There's
No?
only one reaction that is actually anti-Markovnikovs. This one, it's still following Markovnikov, so that means that OH goes to the more substituted side. What about stereoselectivity? Do we have any?
Least substitute? No, but is it, there's like the.
In this case, it actually doesn't matter. It doesn't have a preference either. Now, in this reaction, could we do any rearrangements?
Nope.
No, because we don't have any carbocation intermediates. We have that mercurium ion intermediate. In this case, let's just say no. Remember, from this class until from now on until the very end, whenever you see a carbocation, if you can make it more stable, you're gonna do that. It's expected from you guys to just do it on your own. They're not gonna tell you that you're doing a rearrangement in this case. you just have to do it, but only whenever you see a full positive charge. If it's delta positive, that's not a carbocation, you're not doing any rearrangements, okay? Keep that in mind. So in this case, we know that, again, double bond does the attack, and technically for this reaction, mercury attacks back, but again, you do not get asked about the mechanism. But we're gonna preserve the carbon chain because we know that eventually, basically a shortcut for any of those reactions is get rid of the double bond, is there more carbonicals or anti, and then just follow it and just add the OH to whatever side you have to. In this case, because it's more carbonicals, I'm just adding it right there. So
It's the
I don't,
same as acid catalyzed surgery.
in this case, yes. Mhm.
So it's always gonna be the same.
Not always, because the first one can do rearrangements. If you create a
Okay.
primary or secondary carbocation, then yeah. Okay, very last one, hydroversion oxidation. It's anti-mercapnicals, beautiful, you got it. So that means that the OH is gonna go to the least substituted side. What about steric activity? Does it have any?
Yeah.
It's an addition, exactly. What does an addition mean for this reaction?
Adds the same stuff.
What's on the same side?
Always added thing.
Which added thing?
Oh wait.
OH and what else?
Hydrogen. No.
Yes,
Yeah.
OH and hydrogen, they have to be on the same plane. Do we have any rearrangements at all? Why not? No
Anti-mercapnical
carbocation. It's not because of that, it's because we don't have a carbocation. That's the reason. So in this case, let's just say no. Again, same shortcut. I'm just gonna start by drawing out the carbon skeleton. I know that eventually I'm gonna get rid of that double bond, so I'm not gonna draw it there. And then is there mercapnicals or anti-mercapnicals? Anti, so I'm just gonna place my OH on the least substituted side. And your hydrogen, it's technically gonna be on the more substituted side. And since we know that it's gonna be a syn addition,
Methyl is down. Yeah.
and it's right there. There we go. Question in the back. How did I know that it was a syn addition? Those are just rules that we have to memorize. They're from Orgo 1. The exact reasoning why they happen, I'm not sure. And you're not gonna get asked any conceptual questions on that. Okay, any other questions on addition reactions? Very good. And like you saw, we can just use the shortcut. We don't have to do the mechanism. Just learn, is it mercapnicals or anti? Does it have steric activity? And really important, do we have a carbocation intermediate? So just remember those three aspects and you guys are good. Okay, so now we know how to make alcohols, which is like a good chunk of chapter 11. Now, the next part is doing the complete opposite, getting rid of them. And we're gonna do that by elimination reactions. Now, in case you guys wanna review your notes on this, from Orgo 1, this is chapter 7, okay? And rearrangements in general, they are from chapter 7 as well. But let's start over here.
These are eliminated.
They are elimination reactions, yes. So something that you're gonna see in both examples is that you have some sort of acid, and you're always starting with some sort of alcohol group, obviously. Now, what are the two types of elimination reactions that we can have?
E1.
What's the difference?
The carbon cation.
Yes,
The Oh, I different get it. Yeah. Nucleophiles that
Strength
are
of the
required,
nucleophile.
and the temperature.
and
high
the temperature also
favors
affects it.
elimination.
Exactly. So yes, very important. You might get a conceptual question on this, is that heat is one of the factors that promotes elimination reactions. So please remember that, it's very important. Okay, now again, you're not gonna ask any questions on the mechanism. You just have to learn certain rules. Now, one of them is gonna be dependent on the degree of the alcohol that you have. So let's just start writing them down over here. So if you have a primary alcohol, you're always gonna be following an E2 mechanism, okay? And I want to point out that this is only gonna apply for H2SO4 or any acids in general. There's only gonna be one exception that we're gonna talk about next. But in general, primary alcohol, you just follow the E2 mechanism. If it's secondary or tertiary, we follow the E1 mechanism. Okay, those are just our basic rules that we learned in Orgo 1. Are you gonna ask to show the mechanism? No. Okay, so in this case, we know that we are gonna have to protonate that alcohol group eventually, right? One of the very first steps. Why do we have to do that?
To make it a leading group.
To make it a better leaving group. Alcohol on its own is not really good. But yes, once you protonate it, let's just say that we add one more hydrogen, that oxygen gains a positive charge. So eventually it's gonna go away. You're left with a carbocation. Now, why am I following the E1 mechanism?
Secondary.
It's a secondary alcohol, exactly. So now I have my secondary carbocation, right? Okay, now, could I make it any better?
Yes.
I
No.
do
Methyl.
methyl shift, exactly. So at the end, I'm just gonna have this little guy. Now, once I have my most stable carbocation, now I can just slap that OH group right in there. So that's why we end up with this product that it's missing 2 carbons actually. There we go.
So how does it work wherever you have the carbocation, that's where you put the double bond?
You always want to create the most stable double bond. How do we know we're gonna get a stable double bond? What's the rule?
Tertiary ideal.
No, what about just double bonds? How do we know that a double bond is more stable than another one?
More substitute double bond.
More substituted, more R groups, the more stable you are for alkenes, okay?
So
Now,
the more substitute, like the higher degree carbocation automatically translates to the more substituted alkene.
in a way, yes, but in this case, to make more sense of this, let's talk about the mechanism, okay? Let's just talk about it. Wherever your carbocation is, that's always gonna be your alpha position, okay? That's always your alpha position. And then whatever carbons are adjacent to it, those are just the beta positions, right? Okay. So remember, elimination reactions are all about hydrogens, about removing them. So we're always gonna be dealing with our beta hydrogens, okay? Only beta hydrogens. So technically, we could have 1, 2, 3 different products, right? So you just have to choose the most stable one, which is gonna be the one in the middle, the first one that I drew. Why? Because it's gonna have 4 R groups, okay? So that's how you're gonna be able to tell. Okay, now, usually a question about dehydrations is not gonna be actually like, show me the product. That's not the most common question that I've seen. It's gonna be a conceptual question, and it's actually gonna be about POCl3, which is the next one that we're gonna talk about. And in this case, let's just fill this out. We followed an E1 mechanism for that one, because it was secondary. That's how we know. But remember, whenever you use H2SO4 as your reagent, it's gonna be up to the degree of the alcohol. Okay, that's the main part. Now, POCl3 is gonna be more of a special guy because it's only gonna follow one kind of mechanism, and it's always gonna be E2. Okay, it doesn't matter the degree of your alcohol. That doesn't matter. It's always gonna be E2. Okay, and he really asks you a conceptual question on this. It's just gonna be like pure words. Whenever you do a dehydration with POCl3, what kind of mechanism is it gonna follow? You're gonna have SN2, SN1, E1, and E2. It's always gonna be E2, okay? Please remember that one. And that's why I highlighted that one especially. Okay, so far, questions on dehydration.
So we don't really need to know the product of that.
Of that one? Not really. Let's go through it. We know that eventually that goes away. You're left with a little carbocation there. No, that one is secondary. Are we gonna do any shifts?
No, the product is
Wait, if you do a method,
just adds a double bond.
It just adds a double bond. Because remember, we're following the E2 mechanism. We're actually never forming a carbocation. I just show that part so it's easier to see because it's relatively the same thing that we just saw.
E2 doesn't form carbocation.
Exactly. E2 and SN2 actually, they always follow only one single step. Technically,
in one
everything happens in
step.
one step.
where do you put the double bond? How do you know which side? to put?
Okay, so whenever we're trying to do an E2 reaction, the first thing that you're gonna see is the beta hydrogens. So in this case, we know that wherever the carbocation is, it's gonna be where that's gonna be the alpha position, sorry. Now, the alpha position is always gonna be that carbon connected to the alcohol group. So I'm just looking at those adjacent beta carbons. Do I have any hydrogens to the right?
No,
No, so there's no possible product to the right. So there's only one to the more substituted side. Yes, in this case, yes. We're always gonna follow sides up for this class. Okay, any other questions on dehydration? Yes.
Hydride or membership of
Mm-hmm, yes. That's gonna apply for any kind of reactions. As long as you see some sort of carbocation, you have to do some sort of rearrangement if possible. Okay, we're good? Okay, let's keep talking about some conceptual stuff. Okay, so which of the following alcohols would dehydrate the fastest with an acid catalyst? How would we try to approach that question? What is it asking us for? What are we trying to find?
the one
It's
that
gonna get
would,
rid of the OH.
That's part of it.
the one that would create the most stable carbocation.
Exactly. More
Mm.
specifically, that part. Very important. Remember, this chapter is going to be all about stability. Okay.
So is it
And
E?
B, because it's the Lilith.
B or D? Which one did we say?
Oh, 'cause
I said-
the
I said
allylic
E.
is only for double bonds, right? So D.
So D.
I say E.
We say E.
Yeah.
What do we say over here in the middle? Do you agree?
I'm saying E.
We're saying E. What do you think?
It's at a tertiary position, plus it's.
Vasquez.
It's resonance, right?
Yeah, and it's allylic to a, aromatic ring.
Because D is vanilla.
Yes,
Because it's directly to that
D
double.
is vanilla.
exactly. Thank you for noticing that.
D is the least.
This is just the vanillic position. So it's the worst one. That's not even an option that we're gonna consider. Now, the other alcohol, the one next to a benzene group, that's gonna be the allylic position, but more specifically, it's gonna be the benzylic position because it forms a benzene group, of course. So this one, it's in the benzylic position. And what kind of alcohol do we have? Primary, secondary, tertiary? Tertiary, we have 3 R groups. So it's benzylic plus tertiary, that's perfect. We really like that one. So because it's the most stable one, it's gonna be able to dehydrate the fastest, okay? Because it can stabilize it better. Yes,
So it's allylic, but since it has the ring, it's benzylic.
yes,
Yeah.
it's just another term. They're basically synonyms. The only difference is that one of them has a benzene group, the other one doesn't.
And also that carbocation is tertiary, so it makes it
Mhm.
less. Okay.
So yeah, like it's tertiary, it's gonna have that resonance stabilization, it's perfect. in
So
this case.
what if it wasn't tertiary, but it was still benzylic?
It's still gonna be really stable and we would choose that one.
Benzylic is always the most.
Benzylic, yeah, that's gonna be the most stable of all, let's say. So let's just write them here, actually. Let's write benzylic,
More stable than, okay.
allylic, yes, because it has that extra resonance pad, so it's gonna be able to stabilize it even more. Then we have tertiary, secondary, primary, and we have vanillic. Okay. Again. This part, very important. You guys should remember that trend. Okay. So far, any questions? Okay, quick recap. How do I know that a double bond is more stable?
If it's allylic.
How do I know that a double bond is more stable than another one?
It creates a more stable carbocation. Oh, the
I'm
more
not talking about
substituted-
reactions.
The more substituted double.
It's just
bond,
the more
like-
substituted double bond. Exactly. The more R groups you have, the more stable the alkene is gonna be. Okay. For hydroboration oxidation, what are the rules that I have to follow? It has 2. What are they?
The OH is, goes to the more substituted. And
No, it's anti, so it goes to the least substituted side,
Mm-hmm.
right?
And what's the other
OH,
rule?
It's syn addition, so it's the same. side,
Beautiful. Exactly.
And then, yeah,
Yes, what about oxymercuration, demercuration?
That's Markov. So the OH goes to the more substituted side, and that's similar to acid catalyzed dehydration without rearrangement. The same thing.
Beautiful. Yes,
If
you
you
guys
have
got
a-
it.
Primary carbocation.
You got it. Okay. Any other questions before we move on to the next topic? We're good? Okay, let's see. So next topic, again, you see my dog, that's on your first exam, okay? Okay, so let's talk about reactivity of carbonyl groups.
First one's the most, yeah. Wait, what?
Okay, let's talk about the concept first. So reactivity of carbonyl. So for this chapter, we're basically just going to be touching a few of them, which are going to be your ketones, aldehydes, esters, and carboxylic acids. Those are going to be the four main ones that we're going to be talking about for this chapter. Later on, we're going to talk about all of them. But for now, don't worry about them. Okay. But reactivity of carbonyl. What do we think are going to be like some of the characteristics that we're going to be looking for? What does it make it more reactive? Resonance? What else? Why are you naming everything?
The number of substituents attached to the carbonyl.
We're getting closer.
Weight,
The weight, we're getting closer.
Electronegativity.
We're getting not that close.
no,
We're getting, where are we? What do you think?
polarity,
IMS?
Intermolecular
points of contact.
acidity.
No,
And the correct answer is.
it's something that we talked about in Orgo 1 like so much. Steric hindrance. The one that has less steric hindrance is gonna be easier to attack.
Okay.
Therefore, it's gonna be more reactive.
Mm-hmm.
Oh, how big it is, right?
Yeah.
Like
No, no, no,
turkey
no, the
tops,
bulky,
even though
but
it's
in the
not
sense
gonna-
that there are more
Based
substituents
on-
surrounding it, so that's reactive. There-
Steric
Other,
hindrance.
other,
Stabilize
other
the middle
elements won't be able to like really get there.
Because remember, if you have more R groups around the attacking side, like it's gonna be a lot more harder for the nucleophile to get to it.
Yeah.
Like
Right.
there's no way, like it's just way too bulky. It is way too much steric hindrance. So again, that trend is just gonna be followed. It's gonna be based on steric hindrance. And technically it's also gonna be talking about electronics, but we're not gonna get to that aspect yet. We're gonna be talking about electronegativity and all of that, inductive effects, all of that. But we're gonna be talking about that on chapter 16. So we're not there yet. Okay, so in this case, we have the first one. What kind of functional group is it?
Carboxylic acid.
Carboxylic acid. Next one.
Aldehyde,
Next one.
ketone, no,
Ether.
Ether.
Ester.
Ester. Very last one.
ketone.
That's your ketone. Exactly.
So wait, the third one, ester,
Third one is ester.
what's,
Ether is whenever you just have like a single bonded oxygen to R groups. You
okay,
have something on ether side, there's no double bond around it.
Your restate on steric hindrance principle, like the bulkier it is, it's the more or the.
So actually, let's do a little trend over here. So less steric hindrance is gonna equal to a higher reactivity for the carbonyls. Okay, so, and actually, let's write down the names, just in case. Acid, next one is your aldehyde. We have our ester. And we have our ketone that looks like a key.
how does it look like a key?
Yeah,
How?
it does look like a key. That's one of the little mnemonics that one of the tutors used to use to help students
Explain,
remember.
show it.
It looks like an odd key, but
Exactly,
like an
something
old
that don't
key.
you know what I mean?
Thank you.
What part?
Either way, we're getting sidetracked with a key part.
And you hold it for like the two
You
big
hold the
things and you turn.
oxygen.
It looked like the sword hilt, like.
You hold the
Yeah.
oxygen.
Okay, the way the key works is not relevant to the actual class. Okay, so out of those four carbonyls, which one is gonna be the most reactive?
The ketone, I would
Okay, we see the ketone over here, aldehyde, middle part, what do we think?
Oh, right, aldehyde is
It doesn't have the methyl, yes.
as a hydrogen.
The hydrogen is hiding, that's how I think about it.
So based on
my
theory,
God,
it would be 2, 4,
Serious.
then 1, then 3.
You got it, yes.
Okay.
Based
So-
on steric hindrance, but not acidity, not resonance.
We're just looking at the steric hindrance.
Okay.
So yes, like your aldehydes, like you have a little hydrogen. That's such a small atom. There's no steric hindrance. Ketones,
The first
that's when you start to get more bulky, right?
the-
Now, next ones are gonna be with oxygens. What's gonna be bigger, oxygen or carbon?
With oxygen.
It's gonna be oxygen. So that's where they're gonna be like the last ones. Okay, they're gonna be not as reactive, let's say.
How come, so what's number 3? Ester?
It's gonna be the carboxylic acid. Because we're between just two oxygens, so we're just looking at the connections that those oxygens have.
So the
So-
ester has more steric hindrance.
Yes, because of that R group. And then carboxylic acid, baby little hydrogen. Okay, any questions on this? Yes, in the back.
Sure.
Because the aldehyde has a little hydrogen. So because the hydrogen is such a small atom, there's not that much steric hindrance. But in the ketone, we have two carbons attached to other groups, right? So there's more bulkiness in there.
Question,
Yes.
why isn't the ketone the most reactive in the sense that there's 3 methyls, I mean, there's 3 hydrogens on each of the methyls, so that's more like things to react with.
So you are correct. And actually that's going into some reactions that we're gonna see on chapter 17 or 18.
So is it like close to each other in reactivity or like in a sense that?
They're close to each other, yes. But as far as like this chapter, at least, we're just talking about steric hindrance. So again, aldehyde's very small, less steric hindrance, so they're more reactive, yes. Aldehyde's the most reactive. Yes, number 1 is most reactive.
And I don't know if this is like part of the test, but reactive with what?
Whatever.
We're gonna see that next. We're gonna be talking about those reactions.
They're like DH3 or all that good stuff,
No, they're gonna be some other type of reactions.
some other type of.
Yeah, those reactions are only gonna happen with pure carbon-carbon double bonds. Okay, it's not gonna be with any kind of double bonds. It's just carbon to carbon double bonds. Okay, but let's practice our knowledge with those molecules. So I'm gonna give you guys 3 minutes to discuss it with each other. Just look to your left, look to your right, talk with each other, or maybe look to your back. But talk with each other, figure out their ranking. So again, 3 minutes, really quickly, just talk with each other.
Okay, then next is 4. Oh, least bulky is number 4. It's got 2 hydrogens. Next is
Then this is the worst.
Then is 5. Then is, what do? We did all 2. No, we did 4, 5, 6,
We're ready.
1.
Can we start new groups again? Just the win.
We wanna do the competition again?
Like,
No. We're gonna do the competition Monday when we review for the exam. Okay,
I don't think which percent is.
not yet. Well, we're talking about the competition, while we're learning them, we're not doing a competition.
Wow. No. Yeah, there's no A.
Like, how do you say?
A,
That book.
Head,
No, I gotta go though. I gotta go.
That's how you pronounce it. And then how do you say your last?
You're doing a
Okay, so pretend you were in a Coke commercial, right? You did regular.
My favorite is
See, those were on the.
Oh, no, you just drank some Coca-Cola. You're refreshed. And then,
You going low, go high.
yeah, and
Alright.
more or less, yeah.
That's
I
how,
think more, I think,
it's not,
yeah.
You're just speaking from a different part of your throat.
Maybe just like let the Middle Easterns out, like. you got-
Okay, do we need the extra minute that we have?
No,
No? Okay, let's talk about it. What's gonna be the most reactive one?
four.
Number 4, why?
Two little baby hydrogens.
2 little baby hydrants, exactly. There's no steric hindrance there.
Such babies,
Exactly.
like infants.
Okay, what's gonna be the least reactive?
3.
Why do we say 3?
Got
Yes, a whole lot of methods.
What's the name of those? Beautiful, 2 terbutyl groups. Okay, what's gonna be the second most reactive?
2,
3rd,
Fifth,
5.
you wanna say all of them, okay?
and then we have 6. And yeah, we got it. Great job, guys. Okay, any questions on reactivity? It seems like it's pretty simple. It's just steric hindrance, and that's it. The smaller you are, the more reactive you are. Okay, are we ready to start talking about the reactions?
Yeah.
Yeah, we're a little,
Just introduce.
I like it.
We get the option,
No.
No, we still have 10 minutes left, so. Sorry? Oh, wait, does someone ask a question in the middle? Sorry. Okay, so over here, we mentioned that we might do like a hydroboration oxidation or something like that with those carbonyl groups, right? So again, quick disclaimer, those reactions are only gonna happen with double bonds that are just made of pure carbon. Whenever we're talking about carbonyls, that double bonded carbon to an oxygen, we're mostly gonna be talking about redox reactions. So oxidation and reduction are coming back.
We never.
Okay. We did them in general chemistry. Oh, yeah, unfortunately, yes. Yes, we all forget about those guys. Okay, so you guys probably remember Ulrich for oxidation and reduction? We just said like, God, we're like dying in the middle. Like we hate
Leo goes girl.
Ulrich. Oh, yeah, that's the reaction that most students have. Okay, we're having flashbacks from Gen Chem. Really quickly, can someone explain me what's oxidation?
Losing is oxidation.
Oxidation.
Yeah. Yes, and yeah. Okay, so that's the technical definition that we learned in general chemistry. But in Orgo, we're gonna simplify it even more because it's just gonna be about the connections that the carbon has. And actually, you were kind of correct when you said the alcohols. You were in a way correct. Okay, so let's quickly talk about this. So oxidation is basically gonna be whenever we go from an alcohol group to some sort of carbonyl group. Why? Because we're increasing the number of bonds between carbon to oxygen. So on the first one, in the forward direction, we're going from what kind of alcohol group? What's the degree? From a primary alcohol to what's the name of the next molecule? To an aldehyde. So we went from 1 bond between carbon and oxygen to having 1 and 2. So we're increasing the amount of bonds between carbon to oxygen. The forward direction, it's an oxidation. And we can see that same pattern from the aldehyde to what's the next functional group? To the carboxylic acid. We still have those 2 bonds from the carbonyl itself, but we also have 1 extra to that other oxygen. So we are still increasing the number of bonds. Therefore, that one is still an oxidation. Okay, so really quickly, let's just do a note here. We increase the amount of bonds between carbon to oxygen.
That's oxidation.
That's oxidation. Then reduction, the complete opposite. So that means that we're going from something that has more to less connections. So it's going to be the reverse reaction in this case. So reduction, and we have reduction.
We need to know the mechanism.
For oxidation, you don't have to know the mechanism. For reduction, it's going to be helpful to know the mechanism.
But he doesn't test.
He's not going to be like Dr. Jermaine asking you the curved error mechanism. No.
So in oxidation, it's just any non-H group. That's technically an oxidation in addition of any non-hydrogen group.
Basically, yeah. Okay, so far, questions on the general concepts between oxidation and reduction for orgo? We're good? Okay, seems like we're good. Okay, we have 7 minutes, we can talk about reduction. Okay, that's good. Okay, so again, dog for 6 a.m. So reduction, very important. And actually, we have a little meme here to help you remember the reagents. Yeah, so we're only gonna have only two reagents, and that's it. Okay, so the list is pretty simple. We just have the sodium reagent, as I like to call it, and the lithium reagent, because the actual names are a little bit long and I don't like to use them. So that's going to be how I'm going to refer them to in SI. So just so you know, sodium reagent, NaBH4, lithium reagent, LiAlH4. There we go. No. Sorry? Yes. So what's the main difference that we see between those two photos?
Gain.
This bigger one.
Exactly. We see the gains. One of them is way stronger than the other one.
Oh, gains, I got it.
Okay,
So what is
so
the gain?
as we can see, the sodium reagent, it's really small, it's really weak. It's gonna be a weak reducing agent. And then the lithium reagent, that's a really strong SpongeBob. So it's gonna be the strong reducing agent. Okay, so let's just start writing them over here. Weak, and this one is gonna be the strong reducing agent. Okay, so again, just remember that photo. You're gonna remember if they're weak or strong. Simple as that. Okay, so in this case, let's look at the little question here. It's asking for the nucleophilic species for both reagents. What do we think it's gonna be?
What is that?
What does that mean? Yeah.
Like the charge.
What it looks like as a base.
More specifically, there's another word.
Nucleophile.
As the nucleophile. Exactly. Do you have something to say?
For some reason, like, we're seeing lithium here, the one would make like trans.
Yes. So that was the other lithium reagent. It was part of chapter 7.
Okay.
It was a hydrogenation reaction. But yeah, don't confuse it with that. It's not the same. That was a liquid methyl reduction. Okay. Okay. So I lost my train of thought. What was I saying?
Nucleophilic species, the.
Thank
reagent
you.
has nucleophile.
That's okay. Okay, the nucleophilic species. So as we can hear by the name, that's going to be the thing, the actual atom that's going to be doing the attack. Now, what they both have in common in here is that little hydrogen. Okay, that's going to be actually the nucleophilic species. More specifically, it's not going to be just hydrogen. It's going to be the hydride ion. So that means that we're going to be dealing with a hydrogen that has a lone pair and a negative charge. Okay, that's going to be the nucleophilic species for both of those reagents. Okay, so far, questions on that? We're just talking about conceptual stuff. Okay, very good. Now, technically, yes, you don't have to know the mechanism. As long as you know the rules, you should be good. The only reason why I'm going to show you the full mechanism for this chapter is because your professor is going to present you with isotopes. So in order to know where the isotope is going to be connected, it's good to know the mechanism. Okay, so that's why we're going to be spending some time on the mechanism itself. But, okay. So since we're going to do a reduction, that means that we're going to go from, let's say, an aldehyde or a ketone to an alcohol group, right? I'm just reducing the amount of bonds between carbon and oxygen. Now, what you have to know is that aldehydes and ketones are very reactive, right? Because we saw that they have lesser endurance as compared to the other carbonates that we saw. Okay, so because they're so reactive, they're going to be able to react with any of those reagents. Okay, they're way too reactive, so it doesn't matter the strength of the actual reagent. So in here, let's just start by writing that it works with both of them. It works with NaBH4 and the other reagent, the one with lithium. It's going to work with both. Most of the time, you're just going to see it with the sodium reagent, but still, it's good to learn the concept behind this. Okay. Now, we're also going to do the same reaction, but we're going to be starting with esters and carboxylic acids. Esters and carboxylic acids, how reactive are they? not very reactive. They're not the best. We have some steric hindrance in there. So that means that because they're not that reactive, they're gonna need something stronger to make the reaction happen. It's only gonna happen with the lithium reagent. Very important to notice that. It only works with the lithium reagent. Okay, so far, any questions behind those concepts? It's basically just putting everything together that we talked about. So far, we're good? Okay, we're good. We have 2 minutes. Okay, we have 2 minutes, so I'm gonna save the mechanism for Wednesday. Okay, and we're gonna be talking about those concepts more in depth.
Thank
So-
you.
Before you guys leave, let's do a little quick pop quiz to see if you guys remember what we talked about. Yeah, pop quiz. What's Markovnikov's?
What's a what?
What's Markovnikov's rule?
It's more substituted, favored.
It adds to the more substitutes.
Yeah, exactly. How do you know that I'm gonna do any rearrangement? Only whenever I-
E1, specifically E1 reaction.
E1, and there's a substitution reaction that we could do. What's the name?
That's one.
SN1, exactly. Basically all the ones. Then what's the difference between oxidation and reduction?
Gaining is reduction.
Well, right, yes, but what about the orgo definition?
Increasing bonds to oxygen is.
Is that oxidation? It is oxidation, yes. The more bonds you have, the more oxidated you are. Okay, awesome job, guys. I'll see you guys Wednesday.
Bet.